Alright, so we've gone through the various representations twice at least, and we'll be using the interaction representation today some more. Defined our green functions and correlation functions in terms of the second quantized operators, the spectral function, and this new one that we're going to see more of today, the time-ordered green function, where it's explicitly defined down here in terms of the theta, and the anti-time ordered green function. We're going to come across those again today using this time ordering operator, where later times are to the, so it orders these two guys with later times to the left. So if t prime is later than t, it flips the order and introduces a negative sign. That's what your time ordering operator does. This is I don't know what this name has. This is a green function Keldysh uses to get rid of one, because we use four green functions: gr, ga, g less than, or before we were calling these gn and gp. We're going to start calling them g less than and g greater than. They only differ by a factor of I. If you look at the definitions, before we had gn and gp, g less than and g greater than, they only differ by these factors of plus or minus I here. And it's easier to work with them when you start working with all the other green functions, because all the other green functions have plus or minus I in front of them. We don't have to start introducing I's and negative I's when we start manipulating them. Yes, Keldysh introduced this. We won't be dealing with this at all. So here are the ones where you can think of this as your GN and your GP that we've already dealt with on the right hand side. Here are the new ones, time ordered, anti-time order, and their relationship to stuff that you already know. And if you just go back and look at the definitions, it's pretty clear that these equations are true. And then we went on to show that explicitly calculate this time dependence using the definition and evaluating DDT of the operator by the using the commutator to evaluate the time derivative, and show that this did indeed satisfy the usual green function equation. This is it in the time domain, and if you Fourier transform the energy, this is it, the one that we've been dealing with all along. So all these equations are consistent with what we've already done in terms of they're going to give you the same equations of motion that we've already been dealing with. I mean, the green function theory is really an adiabatic perturbation theory, in which it's a way to take in, there's a part of the Hamiltonian that you can solve exactly in principle, like the single particle part, and then there's the interaction part that you can't solve exactly, and you're going to have to treat in some way using perturbation theory. So this is the equation. This governs the time dependence of the Schrodinger equation. So that's what you have at time t0. This is how it evolves with time according to the full Hamiltonian. This is the way the unitary transformation between the Schrodinger wave function and the interaction wave function. And so this here is the Schrodinger wave function at some time t. This is the transformation to the interaction one. And then you take it one more step. You introduce in here your e to the minus IH t0, e to the plus IH t0, and you turn this into, transforms this into the interaction wave function. And so this is how the interaction wave function evolves with time. And this is given this special name of propagator, or the S matrix, defined like this. Okay, we did cover this. So it has these nice properties. It's unitary, and it satisfies a group property, so you can cascade them together like that and evolve your system with time. And well, since it's unitary, the inverse is the dagger. So this is something we're going to be using. We're not going to be using it in this form. We're going to derive an integral expansion for it. So this is what governs the time dependence of your wave function in the interaction representation. And we also know that this is the equation of motion for the wave function in the interaction representation. And so you replace your psi I with this, and then this thing is just a constant on both sides of the equation, which cancels out. So this is the equation of motion for this propagator, which you can integrate. And so you go ahead and integrate it, and you get this, and then you can iterate this, and you can start iterating it, and you get this. And as we said last time, the problem with this is that this upper limit depends on the next integration variable, so it's kind of hard to decouple this, what's going to be an infinite series. So we played around with the limits of integration and changed the order of integration, and finally got it into a form where all the limits are the same, everything going from t0 to t. And to get it into this nice form, we have to use the time ordering operator. So we get it into this form using these theta functions. It's going to flip the order, and we can do that with the time ordering operator. So finally, we get this propagator in terms of this infinite series, which looks exactly like, the Taylor series expansion of an exponential, right? And so we could formally write it like this, where what we mean by this is exactly this infinite series. So this is the form of this propagator that we're going to use, because this is basically, a series that we can just use first, second order, choose what order we like to include the interaction. For adiabatic perturbation theory, the adiabatic part is this thing here that you put in so that you break up your Hamiltonian into the single particle term, the interacting term, and you turn on the interaction really slowly, adiabatically, so that initially you're in the non-interacting ground state or thermal ensemble state, and then you turn on the interactions. And if you're in an eigenstate of H0, then using the Gelman-Low theorem, you can be assured you're going to be in an eigenstate of the full Hamiltonian. What you can't be sure of is that if you were initially in a ground state, you're going to still be in the ground state of the fully interacting system, because some ground states don't evolve adiabatically from the non-interacting ground state, and the perfect example is a superconducting ground state. Right? That does not evolve adiabatically from the normal ground state. A phase transition occurs. So when you have a phase transition like that, this adiabatic perturbation theory is not going to bring you to the new ground state. You have to do something more clever than this. What's really important to us is the next section, and this is sort of underlies the whole perturbation expansion of the green function. This is sort of the underlying machinery and conceptual stuff for which you calculate self-energies in negative. So at this point, I'm going to slow down so you can all take notes and do it on the iPads. All right. So, we defined our green functions as some kind of, I just was kind of vague about it. I called it a statistical thermal average or something to that effect. So I just used these angled brackets, and I had where C sub H means it's my operator in the Heisenberg representation. I'll just give it some index. Assume we're using our usual localized orbital basis, so I would be whatever orbital index you're talking about. So I just, I kind of put these angled brackets around it. We had a minus IH bar out front, and then this would have been our G greater than, G greater than. But I just want to now start focusing closely on what we mean by these angled brackets, okay, all right? So what we mean by this is sort of what you usually mean is you're going to trace over something weighted by the density matrix, everything in the Heisenberg representation, okay? I mean, this is what you usually mean by statistical average. You weight by the density matrix, and you trace over a complete set of states. And so at times t0, the interaction is fully turned on. You have the exact Hamiltonian at t0. And so rho h at t equals 0 is a full density matrix. It's a full density matrix. And it's going to be the full density matrix in any representation. It's also rho I, all these transformations, they're all the same at t equals 0, just like they were for the wave functions or the operators. And so at t equals 0, I'm just going to call both, I won't make any differentiation. At t equals 0, I'll just call the density matrix rho. So the t equals 0, which is the full density matrix of the interacting system. We didn't talk about the time evolution of the density matrix. Okay, this is sort of I don't know what you would call it, plausibility argument for the time evolution of the density matrix in the interaction representation. So you've probably seen this kind of way of writing the density matrix. Sum over I with some weight factor, which would be your statistical factor, times psi I would be my way of writing the density matrix in the interaction representation. We know how the interaction wave function evolves with time. This evolves with, if I want to get this thing at t equals 0, this evolves as u 0. So psi minus infinity would be when the interaction's turned off, right? This would be a bare wave function at minus infinity. The interaction's turned off, and it evolves according to my propagator u0 minus infinity. And the other one evolves in the same way. It's got to take the Hermitian conjugate. So this would be u it's going to be minus infinity, taking the Hermitian conjugate. Or did I do that right? It should be 0. So my density matrix, rho, the exact interacting density matrix, is equal to u 0 minus infinity. And I'll call this initial non-interacting density matrix before I've turned on the interaction rho 0. Okay, so rho 0 is the one back at t equal negative infinity before you've turned on the interactions. The other thing we need, that the Heisenberg operator is equal to, and to see that we have to relate two things together. Our original transformation, let's see. So before we had written that the relationship was this, OH of t. I'm trying to think of a simple way without going back and looking at all the notes from the three representations. I mean, I think the inner three terms what does this do? This transforms the operator and the interaction representation back to the Schrodinger representation. And then the outer two terms transform to the Heisenberg representation. Okay, so this, the thing with the red underscore is the Schrodinger operator. And then the outer two terms transfer, were the normal transformation of a Schrodinger operator to the Heisenberg operator. Okay, so what I want to show is that, you know, these two things are equivalent. So how do we show that? We show that by then going back to our initial definition of the propagator. So the propagator, our initial definition of U was this. And so now it's just a matter of comparing, you know, comparing the two, well, maybe three expressions here. So if we look at these two terms here, what is that? That's, well, I've got it's these two terms with t equal to 0 and t0 equal to t. It's these two terms with t0 equal to t and t equal to 0, which gives me my u0t up here. That's u0t. And then if you look at the other term on the right, ut0, well, that's these two terms with t0 equals 0. Right? See that? There's two ways of writing it, and now it allows us to use our U's and our power series expansion to go back and forth between the two representations, which is what we need to do. Okay, you all happy with that? Do you see it? You don't have to be happy, just do you see it? Yes? Okay, good. Okay, so where are we? Okay, so now what I'm going to do is take this and these expansions, and I'm going to put them up into here. So where I have my Heisenberg operators, I'm going to write them like this. My density matrix, I'm going to write like this. And let's write it all out and see what we get. Okay. So if we do that, I guess, you know, I should mention that if you've never seen this before, it sort of always makes me think of Lewis Carroll and Through the Looking Glass, because it just seems like you're going into somewhere that nothing makes sense. It's all topsy-turvy. This can't possibly lead anywhere. You know, it's like so different and strange. But I'd like to reassure people at this point that where we're going to end up is with the same equations we derived in Chapter 1. We're going to do it in a really hard way. Okay? So if you like doing things really the hard way, this is the way we're going to do it. Okay.
I have one question.
Yeah.
The density matrix in the left, isn't it a function of t? The u0.
Well, we just want it at time 0 because that's a full interacting density matrix. When the interaction is fully turned on.
But this expression we are evaluating at any time, right? So shouldn't the left two u's, u0 minus infinity and u minus infinity 0, and we just, or shouldn't we just write that as u t minus infinity and u minus infinity t?
This is kind of the very fine detail. You can spend a lot of time looking at this. Let me say what I've written down. It works. Yeah.
You say we are looking at t equals to 0. So that's why we place t equals to 0 here, right?
Well, at t equals 0, the density matrix is a full interacting density matrix, which is what we want. I mean, that e to the negative a to t, that adiabatic factor is kind of a fake, right? It's not really part of the physics. It's a mathematical device. So we want to evaluate, we want to use a full interacting density matrix to do our thermal ensemble statistical average. But let's just proceed and see where this takes us. Okay, so what can I do with this? Because this looks absolutely horrendous. First thing is that, well, this is a trace, so you have cyclic invariance of the trace. So you can cyclically permute all this stuff around. So what I'm going to do, first thing, is to take this first term and just move it to the last term over here and stick it in here. Take it from the beginning and put it into the end. Right, I can cyclically permute under the trace. And now look at the order in which time progresses. I go from minus infinity to 0, 0 to t, t to 0, and 0 to t prime. And so I can immediately combine these into u of tt prime. Right, a group property of these things. So I go u tt prime, and then I have, so if I explicitly write this in, u of 0 minus infinity, I can, also combine these two guys. So this is just u, and so this is, these two guys combine as u of t prime comma minus infinity. So again, the time goes negative infinity to 0, 0 to t, t to t prime, and t prime back to negative infinity. And so if you draw what's happening there on a contour, on some kind of time contour, you start at minus infinity. I'm going to arbitrarily say t prime is greater than t. So somewhere along here I would have t. The maximum point is t prime. And then you go back to minus infinity. So this is what's going on with those propagators. So I can combine all these together after we can cyclically permute, combine the propagators. We have trace or rho 0, u. So if I say that this is, I'm going to call this my, just call this a time contour. I'm going to call it C prime since it's not the final one we're going to use. So just as with the when we pulled that trick with creating a Taylor series expansion in H prime, and we wanted to just combine all the H primes together, we used a time ordering operator. So I can, if I define a path ordering operator, which puts later points on this path to the left, just like the time ordering operator did on the real time line, then I can put all the U's right up front. And if I put all the U's right up front, I just have this U of minus infinity comma minus infinity if I combine them all together. Now that is the identity, but this is not really the identity because I have to put the path ordering operator in front of it and the C's. And what the path ordering operator is going to do is take the pieces of this integral and put them in the proper place. It takes whatever the time is and it arranges the operators so that they're all in the proper order. Just like the time ordering operator did that for the H primes when we created that Taylor series expansion. So I could write this as, I guess let me not change my notation yet, trace row 0 is independent of time. I don't need to worry about that. You define a path ordering operator, and again for this path C prime, and then I can combine this as e to the exponent minus I over h bar closed loop integral over this time path. And this is just a shorthand notation of writing out the infinite series. Right? I mean, this is what my u, this is what defines the u, these integrals. So this u is the integral from minus infinity to t, then from t to t prime, and finally from t prime back to infinity. And I can combine them all together like that as long as I have that path ordering operator, which is going to split up the pieces of the integral and put them in the right spots. Okay, the path ordering operator will split up the pieces of that integral and stick them where they belong. But this is not a really easy thing to work with, this particular path. We'd like something that is a path that's independent of t and t prime. And the way you do that is we're going to stick in the identity operator. And the identity operator we want to stick in is u from some arbitrary time t alpha to infinity, u from infinity back to t alpha. So we cut our path and stick in this thing, which is going to extend the path out to infinity on the right side. And so there are a couple places we can cut it. I mean, the obvious one would be to cut it, say, right after t prime. If you cut it right after t prime, you would have, t prime. You go to infinity, and then you just come back. But in all cases, so minus infinity to infinity. You could also cut it, say, in between t and t prime. So if we cut it in between t and t prime, you go to t, you go to infinity, you'd come back, t prime would be sitting along here somewhere, and you go back to minus infinity. But in all cases, you're always going to plus infinity and back to minus infinity. And also, you could cut it before t, in which case you'd just go out to infinity, and you'd come back, and somewhere along this, you'd have t and t prime. You're going to see that all these choices give you different green functions. This one, since everything is under the path ordering operator on the upper line, since you're going backwards, the path ordering operator would just become the anti-time ordering operator. So if t and t prime are on the upper path, then the path ordered, I guess I haven't mentioned that these are path ordered green functions. I guess I'm jumping ahead of myself. But the path ordering operator would just become the anti-time ordering operator on the upper path. On the lower path, or on this, the path on this guy here, on the path, since t prime is on the upper branch and t is on the lower branch, according to the path ordering, t prime always is occurring at a later time than t. And so for this, the path ordering operator, if you have, your path ordered operator, C of t, C of t prime, dagger, for this particular path, that just equals C dagger t prime C of t. No more ordering operator because the ordering is fixed. T prime, for this particular choice of t prime on the upper, t on the lower, t prime is always later in terms of the path ordering than t. And so this just becomes your G, what we used to call Gn, or now we're going to call it G less than. This, your path ordering operator becomes the anti-time ordering operator of your C of t, C dagger t prime, which is this anti-time ordered green function, tt prime. And this guy here, well, on the lower path, the path ordering operator is the same as the time ordering operator. So this is just your path ordered C of t, C dagger t prime is just going to become your time ordered C of t, C dagger t prime, which is just your time ordered green function, tt prime. So your choice of path, I guess there's one more we didn't do. We could also choose t prime, t here, and t prime down here, and then you have C of t, C dagger t prime. For this case, t is always later than t prime, so that's just equal to, the order doesn't change, C of t, C dagger t prime. I'm leaving out all the constants, the IH bar stuff, which will just give you your G greater than tt prime, which before we were calling our G sub p, tt prime. So depending on the path, we get these four green functions, G greater than, G less than, GT and GT bar, and then just a moment ago, sort of looking ahead, and that's why I wrote them down earlier, I wrote down the relationships that relate GT and GT bar to the ones that we really want, GR, GA, G greater than, and G less than. Okay, so we're jumping ahead. So this is, we want to extend the path, deform the path, if you will, to go out to infinity and back. the way we want to do it is to insert this identity into the path. Where we insert it is going to determine the type of green function we're going to get. But we really don't have to worry about that now. We're just going to insert it and let the path ordering operator take care of it. So the new path, the one that we will be using, this Keldysh contour, goes from minus infinity to infinity. So this is your Keldysh. Or Keldysh path, or whatever you want to call it. This is what I'll call my path C, the final one we're going to use. And really nothing changes. It's just that this is when I write my when I write this expression now. The path is now the Keldysh path, and all I need to do is get rid of my prime here. And so this is defined over the Keldysh. The path ordering operator is going to take care of where those pieces go in between the C and C dagger. And once we're done our perturbation theory, we go in by hand and we say, okay, we're going to let T and T prime lie here, and then we figure out what we get, and then we say, okay, and we have this thing, these four choices that we already went through, four possibilities of where T and T prime lie. And we'll sort that out. So this is the thing we're going to evaluate. The next thing is to define some H prime. And the H prime we're going to use is the one we know and love. It's the H prime for including a lead to a device. So the first example, will be this one that we're pretty familiar with. So we're going to have a device. It's just a single site. There's our device connected to an ideal lead. The perturbation will be our two matrix elements, our T10 and T01, T10 and T01. And so our perturbation Hamiltonian H prime is equal to T10 C1 dagger C0 plus T01 C0 dagger C1. Right, that's going to be our H prime that we're going to use in that exponential. So again, I mean, we've done this before. We're treating those matrix elements as our perturbation, which gives us this perturbation Hamiltonian. But now we're going to do it with this very heavy machinery we've developed. You all ready for this? Okay, so we go ahead and evaluate is the path ordered green function. So this is node 1. That's what I mean. That's my device. Right? This is 0, -1, etc. So G11 is the green function of my device because my device is just a single site. It's going to be the path ordered green function for my device, and that's equal to minus I over H bar trace of the rho 0 path ordered operator of this same exponential that we have up there, minus I over H bar, all this stuff. I guess I really don't need to rewrite it. It's exactly what we have already written up there in red. everything's a 1. T, Ci1, T prime, dagger. And this is same thing. Where H prime is now defined as this. It's just, I've now defined what I mean by my H prime, some specific H prime. And so we're going to expand out that exponential to second order. So if I take this exponential and I expand it out to second order, I get 1 for the 0 order term. Plus minus I over H bar. So there it is, the second order. And now I'm going to evaluate the, stick that back in there in the trace and go through and evaluate it term by term. And we're going to have all these products of operators that we're going to have to factor out and figure out how to evaluate it. And the way we do that is using Wick's theorem. But the first one is easy, the 0 order term. Right, the 0 order term, this just gives me my 0 order term. So it's a 0 order, I just get the bare path ordered green function. Because when we evaluate these things, we're evaluating these in the interaction we're evaluating them in the absence of the interaction, right? All the interaction is explicitly included in the exponential. So when we evaluate these operators, they're evaluated in the absence of the interaction. So this is just your bare green function. And I'm going to use the same notation we've always used. Little g's are for the bare green function before we've turned on whatever it is we're going to include previously through Dyson's equation. Okay, that's the 0 order term. That's easy. Let's look at the first order term. The way we evaluate this is using Wick's theorem. Without really going into the details of Wick's theorem, let me just say how to use it. What are the rules that you need to follow? So 1, you can only pair creation operators with annihilation operators. You don't want to pair up time arguments so that, well, let me try to think this through. When we pair things, when we pair two operators, a C dagger and a C, we then can factor it out and we're going to get products of green functions. Right? Each C dagger C, I'll individually put my angle brackets around them and they're going to give me a green function. A path-ordered green function in this case. And what I don't want when I'm done with this is if I look at the possible, I mean, there's not much choice in these terms here, right? If I have to, I can either do this, which we're going to show is not allowed, and if I don't pair the same time argument, then I have to pair. I don't really have any choice in the matter. If I have to pair different time arguments together, that would be the only allowed pairing for this term. Okay? And if I do that pairing, that's going to give me a G, a path ordered. The first term is going to be 1, 0, T, comma S, and then T, 0, 1, and then GP. And the other guy is going to give me 1, 1. 1, 1, st prime. And remember there's an integral over here, over s, ds. So you want the pairing so these guys are somehow connected together. In this case, right, it's sort of like, especially if you think in steady state when they're only functions of the time difference argument, that would look like convolution, a convolution integral over time. And also, all the indices follow, both in time and in the subscripts, right? If you paired them according to this dotted line that I drew, then you would have, G. What would you have? You would have G 1, 0, SS, T0, 1, and then G 1, 1, TT prime. And we haven't even begun to talk about, Feynman diagrams. But this guy, in terms of its time argument, is not connected in any way to anything else. This integral ds. And when you go back and think of what happens, in a C dagger C term when we put the two time variables identical, that just becomes like an electron density or a hole density. It's an integral over all energy. And if you think of it in terms of a Feynman diagram, this green function goes from S to S. This green function over here goes from T to T prime. And this is what they call a bubble diagram for obvious reasons. It's not connected to anything. It's just sitting all by itself as a circle, and it's called a bubble diagram. And the sum of all these bubble diagrams add to 1. So you don't want to pair things up, so you end up, it's also called a disconnected, again for obvious reason, a disconnected diagram. So you don't want to do any pairing that leaves you in a situation like this, where you end up with something that's just completely disconnected from the rest. And I wanted to say, pair different times, but we're going to see later that in Hartree-Fock, and there's a diagram that looks like this, where you do have a green function up here, and this would be your interaction, if you like V of Q, and you've got another green function. So this is, this is a bubble diagram, but it's a connected bubble. It's connected by the interaction. Here we don't have any interaction. At any rate, so I'm not quite sure how to say this except, avoid disconnected diagrams. And now that's kind of vague at this point since we haven't even talked about diagrams. Disconnected, I'll say disconnected, I don't know what to say. Disconnected green functions. But this is what we mean, that bubble diagram. There's something that's sitting out there not connected to anything. And what's the third rule? Oh yeah, and finally, since you're going to turn them into path-ordered green functions, you want to order the pairs with the creation operators to the right. because that's the way we define the path ordered green function. It's like CC dagger. And so we're going to turn it into a path ordered green function. So we need them ordered in that way. And if the total number of interchanges is odd to achieve this ordering, then you introduce a -1. So if number of interchanges is odd, you introduce a -1. And this is overall, so say, up here we have 4 operators, and we're going to order them into 2 pairs, each looking like a CC dagger. So the total number of interchanges required to do that, if it's odd, you introduce an overall sign of -1. Because each interchange, picks up a -1. Every time you interchange, there's a -1. All right, those are the 3 rules. So let's go ahead and do this. Well, after all, okay, so let me erase the dotted line here now so it doesn't confuse anyone. Okay. So this is the only valid pairing here. And similarly on the upper one, the only valid pairing is like, what is it? Like this. These 2 guys. Right, that's the valid pairing, the only possibility. And so let's look at this. Okay, so let's look at the top term. And so if I pair them up and reorder them, I'm going to have T10 times, right, once I pair them, then I'm going to individually take their trace, and I guess I had my integral over ds, and I had a minus I over h bar squared times the whole thing. So if I give each one of these terms a -I over h bar, this is the definition of my path ordered green function. So it's what I wrote down earlier. This is just, what is this? G, my path ordered green function, 1, TS. This is GP 0, 1, ST prime. And I got my T10s. Always like to put everything in order. The indices should all follow subscripts and time variables. It's always a good way to check. So just like when we first started doing the Dyson equation, and I'm carefully going through this step by step, but just like with the Dyson equation, you see a green function that crosses the 0, 1 boundary. And this is a bare green function. This is a green function when there is no connection between 0, 1. So this green function must be 0. Just like when we did Dyson's equation. And the same thing if you look at this term, the way the pairing is. Right, I'm pairing a 0 here with a 1. This is also going to give me a green function. The second term will also give me a green function that crosses the 0, 1 boundary. And so the first order term gives me 0 altogether. I get no contribution at all from the first order term of the expansion. That's unfortunate because the second order term starts getting kind of hairy. But this is what you have to do. So let's look at the second order term. Let's get a nice clean page here. Okay, the second order term. Well, we just have to write it out. It's kind of painful. T10 times the same thing, all is a function of the exact same thing, all is a function of S2, and I'm integrating H prime of S1 times H prime of S2. Right? The form of H prime isn't changing, it's just the time variable is changing, the integration variable. All times, the whole thing times this C1 of T, C1 dagger, T prime. And so we have to multiply those two things in parentheses out. The first term is going to be 4 terms. So let's call it term. Okay, the first term is going to give me T10, T10, C1 dagger. So I would have, so this is, let me put in my T10 so you can see which ones we're doing. Okay, so I'm doing the multiplying the two terms on the left, the ones right above the other, together, to give me term 1. I guess I can write in C1 dagger, C0, C0 dagger, C1. Okay, now, so let's look at the possible pairings here for this term. So rule number 2 for this case is very simple. You cannot pair operators with the same time variable. Right? You have to pair creation and annihilation operators and operators with a different time variable. So that kind of cuts it down. So we've got there's really only one of the possibilities here. So I could do this, pair this guy with him, and I can pair this guy with him, and this guy with him. That's one valid set of pairings. But if you do that, you notice that I'm pairing over here a C1 with a C0, which is going to give me a green function that crosses the 1-0 boundary, which is going to kill the whole thing. So that pairing will give me nothing. Another pairing would be if I do, what can I do? This guy with him, and yeah, I'm stuck. No matter which way I go, I'm going to end up with something that crosses the device lead boundary. So in this case, these two guys cross, and that'll just give me 0. So there's no pairing, no possible valid pairing that's not going to give me a green function like a G10. It's going to be 0. So this term is 0. The fourth term is also 0, where I have a T 01 times a T 01. When I multiply the two terms on the right together, one above the other, that's also going to give me 0. The same thing is going to happen for the same reason. So only the cross terms where I have a T10 and a T01 are going to give me something. Okay? Which kind of, when you start thinking about all the indices must follow, that's the only possible way the indices are going to follow if I have a T01 and a T10. And so let's look at one of the cross terms. So I have T10 only pair 1 with the subscript 1 with the subscript 1 and the subscript 0 with a subscript 0, otherwise I'm in trouble. So I'm going to pair those two guys together. That's a 1, 1, that's good. I'm going to pair these two guys together, that's a 0, 0, that's also good. And finally I'm going to pair these two guys together, give me another 1, 1, which is good. And that's the only pairing there is which doesn't give me a 1, 0. Satisfies all the rules and doesn't pair a 1 with a 0. So that's it. So now I go ahead and I do my reordering. And that's going to give me, if I put it all back together, I'm going to get, this is a second order term, there was a 1/2 out front. So GPTS1, that's for my very first pairing. The C dagger 1 S1 C1T, like using that G11 TS1. And I'll keep all my ordering of indices, so I'll put in my T10 here. And then I need a 0, 0, so that would be G P 0, 0 S1 S2. That comes from my second pairing here. That gives me that G00 S1 S2. Put in another T, T01, and now my third pairing over here gives me my G P S S2 T prime. So again, this has a nice feature that all the time indices follow one another, T, S1, S1, S2, S2, T prime, and all the subscripts follow one another, 1, 1, 1, 0, 0, 0, 0, 1, and back to 1, 1. If they don't do that, then you better double check what you just did. If we, so this was term, which term was this? This would be called, say, term 3. If we do term 2, I don't know, sorry, 2. If we do the other cross term, we actually get exactly the same expression. I may have to switch the dummy indices S1 and S2, but if I do that, I think I do. I have to switch the dummy variables of integration S1 and S2. When I do that, I get exactly the same expression. And so you can just add them together, and what that does, it just gets rid of the factor of 1/2. Adding the two terms together gets rid of that factor of 1/2. And so this is the final answer for the second order term. So the second order term gives me this. Okay, the second order term of that expansion gives me that. And this thing here has a very familiar look to it. What does that look like, the thing in the underbrace?
Self-energy.
It looks like a self-energy, looks like our usual self-energy due to the lead. And these are the green functions of the system in the absence of T1. So that GP00 is your path-ordered surface green function of the left lead. And this is the exact, so the exact self-energy of the left lead pops out in the second order term. Right, this is not an approximate self-energy. We know that this is actually the exact self-energy of the left lead. And you know, it's happening so nicely because we're doing this perturbation theory on a quadratic Hamiltonian, which in principle should be exactly soluble anyway. And we are getting an exact solution. we're not quite done yet because, you know, this thing, all of these green functions are bare green functions. So if we put this back together, what we have so far, well, let me just, so I don't have to keep writing this out, I'm going to just, from now on, just call this sigma, my path-ordered self-energy, S1, S2. It's my path-ordered self-energy. Okay. So what we have at this point, after our second order expansion, is that the path-ordered green function is the bare green function plus this second order term. Yeah, this is not sigma 0, 0. This is sigma 1, 1, right? It's got to be the initial index and final index. That's sigma 1, 1. Okay. So this is what we have. It looks almost right. If this were a Dyson equation, over here, this should be the exact green function. Right. For a Dyson equation, that would be the exact green function. And we know that if this were like our retarded green function, that would be the exact expression for the retarded green function if we're just thinking in terms of energy when we used to write it. You know, big G was little g plus G sigma big G again, where sigma was the self-energy due to the leads. Right? So at this point we have something that looks like this. GP, I'm just going to suppress time indices and integration be implied. Right. It's not quite there yet. But it turns out if you continue going to higher order terms, the odd terms won't give you anything. The even terms will just, each even term will just give you one more, you know, so the fourth order term would give you G11, sigma 11, G11, sigma 11. So each, you would just generate this power series. The higher order even terms would just generate this power series. And you can sum that power series, and that power series, just carried out to infinite order, is exactly what we're looking for. GP11 is little GP11. That's still GP11 sigma 11 big GP11. Because if I take this equation and start iterating it out, I just generate that power series. Right? So that infinite power series and that equation, that Dyson equation, are identical. And so this is the final exact expression for this path-ordered self-energy, where we just have what I wrote up here, and we just what I wrote up here, and we just replace that last green function with the exact green function like what I wrote below here. Just make that replacement, and that is the exact expression that you generate from this power series expansion, which looks exactly like our old Dyson equation. And so this is the path-ordered green function. We now need to start making some choices about t and t prime to get the green functions that we really need to calculate things like electron density and current. So now we go ahead, there's these four possible choices for t and t prime. And we're just going to go through them and do them by hand and see what we generate. So let's get the thing that gives us all our observables before we called it G sub n. Now we're going to work with G less than, which is only different by a factor of I. So G less than 1, 1 T prime is equal to I over H bar. And so that you get this when you put T prime on the upper path and T on the lower path. Then your path ordering operator will always put the C dagger to the left of the C. Right, because on that path, T prime comes after T. So the C dagger T prime will always be placed to the left of C of T, so you just make that placement and you don't need any more ordering operators there. Okay? So we're going to put T prime, because what we want is G less than, because that's what gives us all these observables that we're after. So this is where we're going to choose to put T and T prime. And now, once you've done that, now you have to go through by hand and choose 4 possibilities for S1 and S2. So, number 1, we're going to put S1 and S2 down here. S1 and S2 down here. Okay? And if you do that, then our green functions are going to become these 3 green functions here. Well, TS1, that just becomes the time ordered GT 1, 1 TS1. Because they're both on the same forward moving path, the path ordering operator becomes a time ordering operator. Sigma P, S1 and S2 are also on the same forward moving path, so this just becomes the time ordered self energy. And S2T prime, well, T prime is always coming after S2 on the path, so this becomes a G less than S2T prime. There is, just to reassure you, there is a more efficient method, but once in your life you're going to go through this without knowing any rules, just breaking this up and doing it by hand. Now this should be T and T prime, sorry. So we're keeping T and T prime where they are, and now we're just going through the 4 possibilities for S1 and S2. So now let's put S1 and S2 on the upper contour. Put S1 and S2 up here. S1, S2. The order of S1 and S2 on the upper contour doesn't matter. It's just important that they're both on the upper contour. Okay, so in that case, what have I got? I've got, so TS1, well S1 always is after T, so this will become a G less than 1, 1 TS1. Well, S1 and S2 are on the reverse moving path, so the path ordering operator up there becomes the anti-time ordering operator. So sigma T bar, S1, S2. And T prime and S2 are also up there, so this will become the anti-time order green function, S2T prime. Okay, now the next 2 are when we break S1 and S2 on the different parts of the path. So T prime. And what are we going to do now? S1 on the lower contour. And S2 up here. So if you do that, TS1, well, I've got a time ordered GT11. What's next? Sigma, oh, that's going to become a, S2 is always after S1, so that'll become a sigma less than. And finally, S2T prime is on the same reversed going path, so that's the anti-time ordered green function. S2 T prime. And the final possibility, so S2 downstairs, S1 upstairs. And so now, what have we got? GTS1, that'll become a G less than. Because S1 is always after T on the path. Sigma, S1 always comes after S2. That's the first time we've seen this, so this will be a greater than. S1, S2. And last one, S2T prime, that'll become a less than. A less than S2T prime. S2T prime. Okay, so that's what happens to the green functions on those paths. Now there's another thing that's happening. Very important thing is that once I do these steps here, even though I've kept the variables S1, S2, these are all now real-time integrals. They're no longer on the path. They're either the integral from negative infinity to infinity, or an integral from infinity to negative infinity, depending on which path I'm on. But they're real-time integrals and real-time variables. Of course, I really don't want to do the integral from infinity to negative infinity, so I flip it and introduce a negative sign. So I introduce up here, both S1 and S2 are on the reverse path. They would both get a negative sign, so they cancel, so nothing matters. The only time you pick up a net negative sign is in this situation, where you have one variable, one integration variable on the upper path. So I'm going to introduce a negative sign and then make both integrals go from negative infinity to infinity. All right? And so for this case, it's going to pick up an overall negative sign out front, and same for this case down here. So that I can have my both my integrals go from negative infinity to infinity. Right? This is just coming about because I'm reversing the limits of integration of one of the integrals. Right? Because on the upper path, I'm really integrating from plus infinity to negative infinity. But I want to write both integrals having the same limits. Okay, so these are the four terms. And now you've got to add them all up and see, hopefully get something So now I'm going to suppress all the indices and just write out the four products that we have. So at this point we have, and what I'm going to do is use those relations that we showed earlier to get rid of all the GTs and GT bars and write them in terms of other green functions and correlation functions. And I'm trying to find where they are. GA. So those four relationships are where we're going to use to get rid of all the T's and T bar operator, all the green functions and correlation functions. First thing I'm going to do is look at this term and this term, simply because they both begin with a little g less than and one has a minus sign. I'm just going to hope that something cancels. That was my approach. So here we go. So the term on the far right, that's already as simple as you can get it. I'm going to now, use these relationships on the second term to get rid of those T-bar terms and write them in terms of something else. So let's see, what have we got? So I have G for the second term. I have G less than. Mention that the self-energies follow exactly the same relationships as the green functions. So these four relationships I wrote down for the green functions. The self-energies follow the same relationships. Okay, so there are the four terms I get. And I do indeed get a cancellation, fortunately. All right, so this term cancels this term. So summing terms 2 and 3, I end up with this down here. So we'll just hold that, come back to this in a moment. Now I'm going to work on the other two terms. So let's work on these two guys. What have we got here? And so that's equal to, okay, so I get one cancellation in there in the parentheses. These two terms disappear. And now with that, I'll then work on, expand out the GT in the front. All right, so what have I got? I've got, at this point, these four terms down here, and these three terms in green up here. And it looks like I have one cancellation. Right, this another color. This term here looks like it cancels this term here. So these two terms down here are part of my final answer. We're done with these. These guys here are going to stay around. They're part of the final answer. I've got three terms left. And so the three terms left, here, here, and here, if you look at them, they all begin with G less than and they all end with GA. Right? They all begin with G less than and they all end with GA. Those three terms are, and if you go back and look at those relationships among the green functions, which are the same as the relationships among the self-energies, you will see that this thing here is none other than the advanced self-energy, sigma A. And so the third term is G less than sigma A, GA. So those are the three terms. And so if we put all that back together, the Dyson equation for G less than, and so if we then go back and put in our time variables, each one of this would be, these triple products are really double integrations. be like T S1, S1, S2, S2 T prime in the time domain. And in steady state, where they're only functions of the time difference coordinate, these are all convolutions, and when you Fourier transform a convolution, it becomes a multiplication in energy. So these, in terms of energy, these are all just multiplications, just the way I wrote them. So in terms of energy, GR inverse for the bare system, acting on G less than, gives me 0. In the bare system, where there is no self-energy, GR inverse is simply E minus epsilon sub D acting on G less than gives me 0. And there's no self-energies around. And so what I'm going to do is hit this whole equation on the left with GR inverse. So I get, little GR inverse. Little GR inverse times G less than. So it kills off any little G less than inverse. And that's going to equal sigma R G less than plus sigma less than GA. And now I bring this over to this side. And GR inverse is E minus ED, so I have E minus ED. Well, let me be more general than that. That's just H. GR inverse is E minus H0, right? My bare Hamiltonian. That's GR inverse. E minus H0 minus sigma R acting on G less than is sigma less than GA. And if you remember the equation of motion for Gn, it was E minus H0 minus sigma R. Gn was sigma n GA. The only difference between the Gn and sigma n and G less n and sigma less n is the same factor of I. It's the same equation. So we've rederived the equation of motion for Gn through this non-equilibrium perturbation theory. This, of course, is your, full GR inverse. That's the inverse of your retarded green function. Your exact retarded green function. And now I don't know if you've ever seen this before, where this complicated looking equation comes from, this Dyson equation for G less than. Our usual Dyson equation looks so simple. It's like, G equals little g plus G sigma big G. This is a lot more complicated, and now you understand where it comes from. G less than is not really a green function, it's a correlation function. Now, this was clearly very painful, and you definitely would not want to do this every time you did some perturbation theory using non-equilibrium green functions. So thankfully, Landgraf came up with a set of rules to do this factoring of the path-ordered products of path-ordered functions into real-time functions. So Landgraf rules, and we'll stop here because it's getting late. So first, just look at a simple product. If you have a path-ordered function that's a product of two other path-ordered functions, then the real-time functions are like this. D less than is equal to AR B less than plus A less than BA. And for the greater than, you just put in a greater than everywhere there was a less than. AR E greater than plus A greater than BA. The retarded and advanced green function, their form does not change. It's just AR, BR, and DA is just AA, BA. So that's how you turn a product of path-ordered functions into real-time functions. Now we had triple products, so fortunately you also did the triple product. So if you have a triple product, dP is AP, BP, CP, then D, just so I don't have to write it all. Okay, I'll just write it now. D less than is A, R, B, R, C less than plus AR, B less than CA plus A less than BA CA. And for, again, for the greater than, wherever there was a less than, you just replace it with a greater than. It's the only difference, just like above. And the retarded and advanced, again, they have exactly the same form. You just replace a P with an R or an A, AR, BR, CR. And so if you look at these rules for factoring these path-ordered products, and you look at our green function, we derived that G less than was little g less than GA. That's what we derived, and you can see it follows Langris rule for D less than, which I could have just used right away, but then you wouldn't have learned anything. You would have just had one more rule, but you really wouldn't understand where the hell this came from. Now you know. You've gone through the gory, and now you know why you want to use this rule, because it's really painful to do it by hand. Okay? And also you can see right away, looking at the rule for the advanced and retarded one, our path-ordered self-energy looked just like, our path-ordered Dyson equation looked just like a normal Dyson equation, which immediately tells you that the path-ordered, the Dyson equation for the retarded green function is exactly the one we know and love. That's little gr, sigma r, big GR. Right? Just using Langris rule. Product of three path-ordered functions just becomes three retarded functions. And so we immediately have the Dyson equation that we've always used for the retarded green function. So we've gone, from the path-ordered, going through the whole path-ordered thing, we've rederived the equations that we've always used. If I hit this one on the left with GR inverse, I just get the equation of motion for my retarded green function, E minus H0 minus sigma R, acting on GR equals the identity. And so we've rederived all the equations, and these equations are identical. They're the same matrix equations that we've derived in Chapter 1 using far simpler methods. So I guess that's good. I've dragged you through the whole Keldysh contour and that. And next time we'll do phonons.